Welcome to MathandBolt. So starting today, we work on a fourth type of variable separable form, meaning if we have a differential equation given by dy over dx equals to some function of ax plus by plus c. To solve such a differential equation, this is not exactly in the variable separable form. What we will do, we will substitute ax plus by plus c equals to some other variable v, and that is going to help us convert it to a variable separable form. So let's try to do that with the help of an example. Let's say we have our first example given by the inverse sine function of dy over dx equals to x plus y. Now we'll take the sine function on both sides, so that will give us dy over dx equals to sine of x plus y. So clearly we can see that the term on the right hand side is a function of x and y, so it's x plus y. So what we will do in order to solve such a differential equation, we are going to assume let x plus y be equals to some variable v. Then we're going to differentiate both sides with respect to x. So differentiation of x with respect to x is 1. Differentiation of y with respect to x is dy over dx equals to dv over dx. So from here, we isolate dy over dx, so that will be equals to dv over dx minus 1. Then what we will do, we'll use this instead of dy over dx in a given differential equation and substitute x plus y with v. So that means we will now get dv over dx, so this is what we have done, dv over dx minus 1 equals to sine x plus y will be v. So that means we have dv over dx is equals to 1 plus sine v. Now what we can do, we can separate the differentials. 1 plus sine v equals to dx. So this is now in the separable form. Although our given equation was not in the separable form, what we do, we applied this technique. We substituted x plus y equals to v, differentiated both sides with respect to x. That's some manipulation, and that gave us the differential equation in the separable form. So now our task will be to integrate both sides. So let's do that. So we have dv over 1 plus sine v. So that's equals to dx, or simply we can rewrite it as dx is equals to dv over 1 plus sine v, and we integrate both sides. So integration of dx will be simply x. Now to integrate dv over 1 plus sine v, we are going to multiply and divide with 1 minus sine v. So that will be 1 plus sine v multiplied to 1 minus sine v integrated with respect to v. So 1 plus sine v times 1 minus sine v, so that's an identity, a plus b times a minus b, which is simply equals to a squared minus b squared. So we have 1 minus sine v whole divided by 1 minus sine squared v dv. And again, 1 minus sine squared v, that's an identity. We know that cosine square v plus sine squared v equals 1. So this will be 1 minus sine v whole divided by cosine squared v dv. Further simplification gives us 1 over cosine squared v minus sine v over cosine squared v dv, which is equals to integration secant squared v dv minus integration, so sine over cosine, so that will be tangent of v times 1 over cosine v, which will be simply secant v dv. So this is x. So finally we get x equals to, so integration of secant square v, so that will be tangent of v minus integration of tangent of v times secant of v, so that's simply secant of v plus the constant of integration c. So this is our solution, but we have to replace v with x plus y. So we'll get x equals to tangent of x plus y minus secant of x plus y plus the constant of integration c, and this is going to be the required solution to our given differential equation. So let's do another problem. So we have dy over dx equals to cosine of x plus y, which is quite similar to the previous problem, except here we have a cosine instead of a sine function. I'll go the usual way. So we'll suppose let x plus y equals to variable v. Differentiating both sides with respect to x gives us 1 plus dy over dx equals to dv over dx, and isolating dy over dx gives us dv over dx minus 1. So we'll substitute this into a differential equation. So we have dv over dx minus 1 equals to cosine of v, or simply dv over dx equals to 1 plus cosine of v. Separating the differentials, we get dx equals to dv over 1 plus cosine of v. Now this is in the separable form, so we can integrate both sides. We can use the same trick as the previous one, where we can multiply both numerator and the denominator of the term on the right hand side with 1 minus cosine of v. But I'll take a different approach now. What I will do is we'll use the fact that cosine of 2v, so that's equals to 2 times cosine squared v minus 1, and if we use the half angle formula, so that's simply cosine v is equals to 2 times cosine squared v over 2 minus 1. So we'll use this equation and replace 1 plus cosine of v, so that will give us integration dx equals to integration dv divided by, so 1 plus cosine of v will be 2 times cosine squared v over 2. Fine. So that means we have integration of dx, that's simply x, half integration. So 1 over cosine squared v over 2 is simply secant squared v over 2 dv. So that's half multiplied to integration of secant squared function. So that's tangent v over 2 divided by half. So this half came because we have a v over 2 here, and this can be verified by using the method of substitution plus the constant of integration c. So the half and half gets cancelled, and we get x equals to tangent of v over 2 plus the constant of integration c. We'll replace v with x plus y. So that gives us x equals to tangent of x plus y whole divided by 2 plus c, and this is the required solution to a given differential equation.